Hello everyone, let us start our 15th lecture. So, in the last lecture we said that we will start with heterogeneous nucleation, which is very much practically observed. Now, whenever we are talking about heterogeneous nucleation, uh, it actually talks about transformation on some existing surface. And in the last instance, whenever we talk about heterogeneous nucleation, first we need to understand homogeneous nucleation. So, in case of homogeneous nucleation, the nucleation, that means the phase formation from parent phase, does not need to form on some surface. Rather, when it forms, it creates the interface between the parent and product phase, and there are no more interfaces coming into picture during the transformation. So, that makes it clear that whatever discussion we had, that means in case of liquid volume, if we have a formation of a solid, okay, and that time this solid liquid interface is the only interface. This is the only interface which is solid liquid interface. And the total energy requirement for this interface creation is coming from the volume free energy change, which is the thermal factor. And that means the expression what we have received, what we have got, del G r is equal to minus 4 pi by r q delta G v plus 4 pi r square gamma S L. So, this expression, this is the energy supplied, which is due to the thermal gradient. Thermal gradient means from T m to a temperature where transformation is taking place, and this is the surface energy which is being created during the transformation. This is a classic example of homogeneous nucleation, where it does not need to form on any surface, and it can be practically possible, but though we need to do very sophisticated experiments. For example, let us say whenever you have solidification from a liquid, our common perception is we need to pour it in a mold. Okay. For example, if we would like to form, let us say engine block or engine head, or let us say manifold, exhaust manifold or clutch housing. So, those are auto castings. So, what you have to do? You have to melt the metal, okay, and then also you have to create a mold, and inside that mold you have to also place core in order to make hollow parts in the casting, and then you have to pour that liquid metal into the mold. So, whenever metal is poured into the mold, the liquid metal, it starts solidifying, but the solidification is hastened or is does become easy because of the already existing mold surface. So, the solidification is easy on the mold surface. So, that there we have some sort of assistance from the mold. Okay. But then how do we avoid that particular, whenever we have, that means it is also solidification, the casting example, but in case of homogeneous nucleation of solid in a liquid, if we would like to do it, we have to also avoid that mold surface. Now, the mold can be acting as a container, but here also somehow can we avoid the container. Okay? If we avoid the container or mold, I can create an instance where I do not be having any assistance from mold surface. So, if we do not have any mold surface assistance, the solidification mode would be a homogeneous mode, and people do levitation study. So, the liquid metal droplet is created, and that the droplet does not have any surface, does not have any mold surface, it is a containerless solidification. There we do experience homogeneous nucleation. So, but as we have mentioned that the mold is required for any casting, okay, that particular mold surface would benefit casting. Okay. Now, we have to see whether it does benefit or not, because we have seen that the mold surface does get the first solidification. We will now go into that part where the solid will not form in the bulk of the liquid. Rather, if this is a controlled volume, is a volume which is closed volume, let us say. So, this closed volume I can also make it like these are all my mold, okay. And there I can also have a situation where the solid is forming on top of this mold. Okay. So, this is my solid which is forming. Now, interestingly, let us assume that the solid is basically a spherical cup. Okay. Now, if we have a sphere, okay, now this sphere, if you see that if we truncate that top sphere, okay, so then it would become a spherical cup, okay, and that cup will have radius of r. Okay. So, now if we consider that this cup is forming, that means this is the part of solidified portion and this is the mold world. This is the mold world. So, this is exactly replicating this scenario where this cup is forming on top of a mold, but if you connect that particular cup, if we complete that particular cup, it will form a sphere and that sphere radius is r. Now, if we have this situation, so now this is my mold, let us say, and this particular thing is invisible. This is invisible. So, that means this part is not there, but if we complete that, it will become a sphere. Now, this is mold now. Last time it was solid and liquid interface. Now, we have mold, we have liquid and then we have solid. Now, this situation is interesting situation because before the solidified portion, everything was liquid mold interface. So, everything was liquid mold interface. Now, whenever this solid is forming on top of this, if we try to see in 3 dimension, it can look like this. So, this is my this kind of stuff it will form. So, these particular section, that means if we try to see a projection on top of it, if I look at from top, it will form a circle. This will form a circle of some radius r, let us say. So, this was r and this is capital R. So, this is my capital R and this is my small r. So, this is that cup, this is that cup. So, now before formation of this solid, everything was liquid metal interface. Now, after the solid forms, these particular interface, this particular zone, that means this particular zone, we are forming a liquid, not solid mold interface. So, here we are replacing these particular interface with solid mold interface. And of course, we are creating another interface which is solid liquid interface, which is this one, which is this particular spherical cup. So, this is solid liquid interface is created. This is creation, this is creation. Now, what happens to this interface within this zone? That is destruction. That means, it goes out, it is destroyed. So, now whenever we have this kind of situation, two interfaces are created, one interface is out, but there is one more interface which is this one at this particular junction we have another interface. So, interface energy, if we consider this is interface energy, so we can also relate it to interface tension. So, which is nothing but force per unit length, and here it is energy per unit area. So, if you do the conversion, you will get it, surface tension. Now, that means it has a directional nature. So, now if I do that particular operation, so this is this particular force which is gamma SL is towards this is gamma SM LM. So, because though this zone, this particular interface is out, but this zone we have that interface, and another interface which is SM, which will be acting this way. So, now we have situation like this, and then this angle we call it as theta. Now, this theta is called as contact angle. Okay. So, this contact angle will decide what would be the effectiveness of this mold wall for the precipitation. Okay. So, now let us do this analysis, then you will see that yes, this mold wall all tries to bring down the total energy requirement for solidification or phase transformation. This will be valid, though we will do it for solid liquid, but this will be also valid for solid transformation. Okay. So, first do this particular treatment in case of solid liquid. So, now if we try to do the relation between, if I try to plot it again. So, this is solid liquid, if we have this arrangement, now this is also theta. Now, if we do a solid geometry, so then you will see that this also become theta. Now, in order to, if we try to find out what could be the relation or the balance between these three forces, we can have a simple relation, which is gamma Lm equal to gamma Sm plus gamma Sl cos theta. So, this is relation number 1, this will be very vital, and if you see this dotted portion, this is the bigger sphere, okay? And this sphere, if you cut it, it will form a lens kind of thing. Okay? Now, this will be used for our treatment. Now, second case, if we try to understand the similar relation what we have gotten in case of homogeneous solid liquid reaction, solid liquid transformation. So, if that is the volume V L, and if this is V L, and if G L is the free energy per unit volume of that liquid, and this is at temperature T, which is less than T m. So, then we can get to another instance where solid will form, but that case solid will form on top of that mold wall, and then the volume of this solid would be V s, and the liquid volume would be V L minus V s, and here the assumption is there is no volume change during this transformation. Okay. So, that means the del V equal to 0. This is an assumption. Okay. Though it does not happen, there will be whenever solid to liquid or liquid to solid transformation happens, there will be a definite volume change. For example, in case of water, volume increases during solidification, that means liquid water to solid ice, the volume increase happens. But in case of liquid metal, for example, aluminum or iron, okay, the solid, when solid forms, the volume decreases. That is what you have sinkage problem in casting. Now, if we have this assumption, but we are taking this assumption to have a very easy treatment to this problem. Now, this is G 1, this is G 2. So, that means G 1 to G 2 the transformation is taking place. Whenever I am trying to calculate G 1, it is the same calculation mode V L G L, and similarly G 2 would be V S G S, and G S is the free energy per unit volume of that solid, plus V L minus V S, this is the remaining liquid G L. Now, it does not stop here, we have already created interfaces, and the interface, the relation is this interface initially was liquid mold, which is getting replaced with the solid mold interface. That means, one part would be negative, and we are creating one more interface, which is this one. Okay. So, that means, there would be two interface contribution, one is gamma S L into A S L. Okay. So, the surface area of this lens, okay, plus you are creating this interface also. So, this is gamma S M and A S M. Now, this interface is replacing the previous interface, which was liquid metal. So, that means, the area would be same as this, but the interface energy would change. So, minus gamma L M A S M. Now, finally, if I try to see what would be the free energy change, the way we have calculated, it is G 2 minus G 1 equal to minus V. If you do that, you will see this is plus, this is V s plus gamma S L A S L plus gamma S M A S M minus gamma L M A S M. Now, since we have this expression, we can replace gamma L M as well as S M with S L. So, we can gamma S L would be equal to, we can do it like this, cos theta would be so I can replace this term with cos theta, because if you take the minus out, the gamma Lm minus gamma Sm whole the bracket, and then this would be the common factor. So, it will come like this. If you do this little calculation, you will get this. So, this is my final expression. So, it is on the basis of this R. So, I can also put it as R. Okay. So, in case of homogeneous nucleation, the only difference was this was not there. This was not there in case of homogeneous. Homogeneous nucleation, it was not there, but in case of heterogeneous nucleation, that means when we have a mold surface where the solid is forming. So, we have this creation, but this particular area is also not the total surface area of a sphere, rather part of that surface area, and at the same time this V s is not 4 by 3 pi r cube, rather this is the volume only of this particular portion, not the entire portion. So, the entire problem lies in the calculation of this volume and the surface area of this, as well as the surface area of this particular portion, particular region. Okay. So, if we do that calculation, we can definitely get the expression for del G, and this del G R would be expressed in the form of theta. Okay. And theta we have seen is the contact angle. Now, if we do that particular treatment, it will be not that complicated. Only thing is you have to do little small integration, and that time, for example, if I try to see, for example, if I try to take a small segment, let us say I take a small segment if I take this particular, this is to be d phi, and if this is angle phi, then I will just do the integration and then we will get the value. For example, if I try to do the length calculation of this particular length, you will see that this particular term would come r, because this is r sin phi. So, this particular length becomes sin phi, r sin phi. So, this is r d phi, and if I try to see this particular segment, and this is a small portion. So, this becomes, if we can assume it to be a cylinder, small disc, and the volume of the disc would be and the height and this radius, this becomes my radius. So, 4, so pi r square sin square phi, and this height if I try to find. So, if I take if I draw a perpendicular to this line, so then you would see that this angle becomes phi again. So, then this length would be r d phi sin phi again. So, then if I, this is the volume of this small disc, and in order to find the total volume of this particular section, I will just have to integrate over phi equal to 0, that means from here to this portion. So, then phi equal to 0 to phi equal to theta. So, if we solve this, we would get expression. Should I leave it for you to do the calculation, or okay, let me do this particular calculation. And if we do that, then I will take this out. This is V s now. Pi r cube now I can make adjustment, which is pi r cube d phi, and then if I assume that cos phi equal to t, then I can write sin phi d phi equal to dt. So, I can replace this one with dt and this one as t. So, if I do this particular adjustment, so this becomes much simpler. So, if we solve this, and that time when phi equal to 0, t equal to cos phi cos 0 equal to 1, and phi equal to theta, t equal to cos theta. These are the limits, and then the expression would change to 1 to cos theta. So, if we solve this, we will get and then adjustment readjustment 4 by 3 pi r cube 2 minus cos phi minus plus cos q phi theta, sorry, it is theta divided by 4. So, this expression, just a minute, let me have a look at this expression. Sorry, there will be 3 term here. So, this is the expression you would get, okay, if you do the integration. This is the final expression, and this 4 will come because this 3 will come from this after integration, and this 4 you have to take it outside and then also divide it by 4. So, now this is the volume of this particular portion, and we have to find out the area of this particular spherical cup, and that we will do in our next class. I think let us stop here. Thank you very much.